As they said, my name is Javier Fuentes Alonso, and I come here from Uizard. And I'm going to be talking about bringing semi-supervised learning to production. I'm going to start by quickly walking you through what we do at Uizard and some of the machine learning related problems that we are trying to solve. And then finally, I'm going to be talking about how semi-supervised learning can help us out in solving these problems. But first, just a little bit about myself. As I said, my name is Javier Fuentes Alonso. My background is mostly in robotics and machine learning applied to robotics. But since almost a couple of years now, I've been a computer vision research engineer at Uizard, where we are trying to apply machine learning into the design space. And the main problem that we are working on right now is that the workflow for building apps and websites really sucks. You have your idea, you know the product that you want to build, but the process to get there is slow, it's complex, it's really messy. There are a lot of stakeholders, there are a lot of different tasks that doesn't add value to your final product. So we thought, what if we try to apply machine learning to solve some of these issues? And this is where Uizard came out. In Uizard, we take an image of a wireframe. This can be hand-drawn, digitally drawn. Then we pass it through our machine learning, computer vision, and language modeling stack. And we produce a high-fidelity version of the same wireframe. That way, you can prototype much faster. And once you're done, you can export this high-fidelity wireframe, high-fidelity design into a front-end code, into a design file, and continue your journey there. This way, we are skipping all the repetitive design and branding, all the repetitive tasks related to user interface development, making this idea testing and validation much easier and much faster. With Uizard, once you are done wireframing in your design sprint, in a meeting with a customer, all you have to do is pass it through our platform, and boom, you have your high-fidelity prototype. And in early testing, we realized that users are able to do this up to 24 times faster than with the normal workflow. So some of you may think that's quite a cool idea. How did you come up with this? And this actually started with a paper that some of you may have read about. It was called Pigs to Code. And it got from our CEO, Tony, and it got quite viral because it was the first model that featured a fully learned model that will go from a screenshot to actual front-end code. It was basically similar to an image captioning model, where you will have the language modeling task, and then you will also have the computer vision task, where you will pass your screenshot and through some CNNs. And this is the part that I'm going to be talking more about today, the computer vision side. But of course, things have changed quite a bit since 2018, I think this was, to the point that we are not using screenshots, but we are actually using wireframes. And if I tell you like wireframes, hand-drawn, machine learning, how difficult can it be, right? It's just, some sketches. And maybe you have spent too much time in academia, and if I tell you machine learning and hand-drawn, you will think MNIST, and MNIST is easy. So this is probably just, laying some MNIST drawings around, maybe put some lines, and you're pretty much done. Maybe you will change the domain, right, of your symbols, but that's it. But turns out that it's a little bit more complicated than that. And for that, I'm going to explain you what is a line. So a line in our domain is usually some text, but gets a little bit more complicated than that, because text can also be with a lot of other tests, which some of them may be grouped based on different visual inputs. And sometimes you don't even know whether they should be grouped or not. And then you group them and they turn out into an icon for some reason. And then this text group can also be broken down because of other elements and can also have other lines in between, which may or may not mean anything. These lines can be also part of a bigger entity, like a button. These lines can be a modifier for another text in the sense that it will be underlined. But in other contexts, based on what the word says, it can actually change completely the meaning to the point that it will become an input field. And if this doesn't scare you, then you need to bring this to the real world, where even the backgrounds have lines, or the previous drawings from the same piece of papers will also have lines, as well as some fingers. And of course, in the real world, there are way more lines, and the lines appear in domains that you may not expect, like a pizza cupboard or a sandy beach. So if you didn't understand fully what the line means for us, don't worry, it took me some time as well. But what I want you to understand is that when it comes to drawings, the visual representation doesn't match with the semantics of it. And for that, you have these three examples where you have three wireframes with the exact same semantic meaning, but with completely different visual representations. And with this problem, you as a machine learning engineer, you'll be like, okay, that's great. What should I learn, right? Should I go full for visuals, or learn the concept of a line, for which you will need much less data, but it will be, the performance will be much lower? Or should I go full software 2.0, where you will learn the whole semantics of it? And this is a complicated question, because it does not only involve the machine learning side, but it also involves UX, product, and some other stakeholders. But you will say, okay, look, I will just take a decision, and I say, I'm gonna learn at this point. This is what I'm gonna learn, and I'm gonna move on from here. Well, turns out that it's not going to be like that. It's going to be more like an iterative process, where you may expect to also move towards higher performance, but you never know. And this is what leads you to what I call dynamic datasets. And these dynamic datasets does not only mean the regular dynamism in datasets in the industry when it comes to a difference in the amount of data points, but it also means that as you're iterating over how to learn things, you will have to change some of your labels from the images that you have learned before. And this brings a lot of problems. So if we take the traditional machine learning workflow, when you label your data, you train your model, you evaluate, and then if you see that you need more performance, or if you want to fix some of the cases, you may label slightly more data until you reach the desired performance. But what happens if you assume these dynamic datasets? Well, you label your data, you train your model, you evaluate, but when it comes to the iteration over your dataset, it's not like you have to label a small chunk of data, but you have to also update your data if you have to actually change your labels. And this, as your dataset grows, the problem keeps increasing. This is quite a problem, especially if you are a small startup like ours. And there are a lot of different things that you can look at in order to solve this problem, talking about weakly supervised learning, talking about synthetic data. Today, I'm going to be talking about how semi-supervised learning can help us with this specific problem. Because with semi-supervised learning, you have two data sets. On the one hand, you have the labeled data, and then the unlabeled data set. This unlabeled data set will not change over your iterations, which is great. And then additionally, your labeled data will be much smaller than the one that you will need in the fully supervised case, at least ideally. And for the ones that don't know, the state-of-the-art semi-supervised learning models nowadays, they look somewhat like this. You have your labeled data that you apply a supervised loss to, like regular supervised loss, and then to your unlabeled data. To each of those data points, you will first try to predict with and without augmentations, and then basically encourage with a consistency loss that these predictions are the same. Then you will add these two laws together and train it. And truth is, it works quite well. Here you have some results from Fixmatch, which is a model that came up early this year. And they did these experiments on CIFAR-10, where the baseline is 500 labels per class, and you will reach an accuracy of 95% in a fully supervised. And they were able to get, with just 25 labels per class, pretty much the same accuracy. And it goes farther than that. With just 4 labels per class, they were getting 89% accuracy. And with just 1, they were getting up to 78% accuracy. Quite impressive, right? So why are we not all using semi-supervised learning? Well, it works, but not really always. There are some limitations when it comes to applying this in practice. And some of them are placed here. You have the distribution. It makes a huge difference if your unlabeled and labeled dataset have different distributions. Then you have the dataset size. You need quite a big unlabeled dataset in order to get some performance improvements. And finally, most of this latest research has been focusing a lot on the classification task, while in order to get these huge improvements on other tasks, maybe some troublesome, especially in multitask learning, for example. So we are at Uizard, and we saw these results, and we decided that this is something that we need to pursue. This is something that the machine learning community needs in their toolset, right? So we started, we wrote this paper where one of the focus were working on this problem with the distribution mismatch. And one of the problems that we saw with current techniques was that the unlabeled data was assumed to be all from the same distribution. But we all know that this is not the case in the industry, right? The data sets are never clean. So let's say that you're trying to make your animal classifier, but then all of a sudden, for some reason, there are some planes and boats there. You will also try to encourage this consistency over your boats and your planes, which is not really what you want. And we saw that this really helped performance in practice. So we actually introduced this new model that we call out-of-distribution masking, which will allow the model to, in a way, discard all the samples where it's not really confident about, and that way not train on that on those samples where we don't really know much about. This way, the model is able to learn kind of what the classes are, what images are from the classes that you're actually learning, and making the training process much more efficient. And it works. This is some results from some examples that we ran. And here you can see how it compares our method in yellow, called RealMix, with other state-of-the-art semi-supervised learning techniques as we increase the ratio of out-of-distribution samples. And you can see how our method actually keeps the performance quite well, while other methods with just 50% out-of-distribution gets worse performance than in a supervised manner. You can read more about what we're doing here. We also published the code, so feel free to check it out. It's called RealMix. But in conclusion, I hope that I convinced you that drawings are actually quite hard, but semi-supervised learning can really help. And it does not only help in these dynamic data sets or for drawings case, but we truly believe that semi-supervised learning will become a really relevant tool for machine learning engineers, because that will allow you to incur into lower cost, have faster iterations over your product, and this will lead to actual better products. Thank you.
Thanks a lot, Javier. I'm curious to know how you as a research group have interacted with your customers and seen whether some nuances to how they use your product have maybe influenced the types of technical approaches that you used. to improve their customer experience?
Yeah. So right now, like what we are seeing is that there are some people that really gets it, and some people that gets really interested into how this can help them, because they see how, for example, in the context of a design sprint, instead of being able to try out 1 or 2 ideas, you will be able to try out 10, 5 ideas, as many as you want. So there is definitely a lot of interest, and we see, and with this early testing, we saw also how people are really realizing about the value that this brings to their company and to their processes.
And do people use this as like for de novo projects, or do they use it for existing mobile products that they might have been working on for a couple of years that are live with lots of users?
Yeah, it's not only for that. You are also able to define your own design systems in our platform, so that it's not only for the really early stages of development, but it can help you out once you have designed everything around your product to iterate on new features much faster. So it's not only limited to the early stages of ideation.
Yeah. Interesting. And what kind of, do you have any new papers that you're keeping your eye out on and are thinking about integrating into the product, or kind of next steps in the R&D for the product?
Yeah, of course, we want to basically our main focus is in keeping improving this workflow that I talk about and making this as fast as possible. So that means, of course, keep improving this current pipeline, but we are focusing on everything that will help anyone in the design space to be able to create, and also to make to be able to create much faster.
And just a quick point, Javier, I just posted a link to your angel.co jobs, but any specific way that people can get involved with Uizard? Is there specific roles you're looking for, a demo people can try, something like that?
Yeah, definitely. Right now we are in beta, in private beta, but if you go to Uizard.io, then you can sign up for our beta, and then you can also check out the current open positions that we have.
Great, thanks. And just in terms of new things coming to the platform, so at least Nathan and I have been following this story for quite some time, but any timeline or any new announcements we should keep our eyes open for?
We are trying, right now we are trying to make as I said, our platform as accessible as possible, so that basically everyone can actually get started with UI design. So that means that we are democratizing not only for designers this process, but we want everyone to be able to use this. And we are taking some steps towards this goal.
I think we have one question in the chat from Gerald James, who's talking about, or is referencing design thinking techniques that Sequoia Capital have introduced. And he's interested to know if your solution can be applied to story maps.
I'm not really familiar with storylines, but we are currently focusing mostly on the UI design space, so I'm not really sure about that. Sorry.
Cool. No worries. Gerald, you can follow up directly with Javier maybe afterwards, and you can point to the right place to answer the question. Awesome, cool. Well, thanks so much, Javier. We appreciate you taking us through that. Cool paper. I think we'll have some homework to go read up on it. Thanks again.
Thank you.
Great. So from computer vision and UI building, we're going to move into natural language processing, which I think a lot of us are starting to realize that the last 12 months has seen a massive inflection in performance of various open source NLP models. and there's few companies that are better placed to comment on their adoption in the enterprise. So we're really happy to have Malte here from deepset, which is based in Berlin. And the company focuses on really taking these state-of-the-art NLP models and making them work at a large scale in enterprises, and particularly focused on document search and question answering systems. And it's got a few open source projects as well that I'm sure I'll invite you to contribute to. And with that, I'd like to turn it over to Malte to give his presentation. Thanks again.
Yeah, thanks. Thanks for a nice introduction. Very happy to be here today. And yeah, in the next 15 minutes, I would like to give you a quick intro into question answering and how you can actually take that technology from a research data set like SWOT to actual industrial applications. Yeah, as Nathan mentioned in the intro, I'm a co-founder of a small startup in Berlin called deepset. And our DNA, I would say, is best described with we take latest NLP research, pretty much from transfer learning, language models, and in particular question answering, and bring that to the industry, mostly large corporates. And our absolute focus right now is on building neural search software for these enterprises. And our approach with that is really using open source. So we believe everything that you need to build these systems should be open and transparent and free for developers. And our business model then on top is that we provide basically the enterprise features that you need to run this, operate it, monitor it in large-scale organizations, which is then like our business. Beside that, we also were quite early on the language model train and published the first German BERT paper, and are also currently training other architectures, which should be released probably in the next weeks. So maybe let's start a bit with search and reflect on how that developed in the last years. If you think maybe 5 years, 10 years back, search was pretty much typing in some keywords in the web and getting a list of ranked websites. And that was already super helpful. But if you look at modern search, modern web search, it has changed quite a lot. And there are many things that changed, but two that I want to highlight here. You can now basically query in more natural language, and we see that the user behavior is more and more switching into this direction. You can ask natural questions, and instead of only having ranked websites, you find often like the answer that you're looking for already on the top, and there's like a very granular text. And this is basically what we are also working on. And the beauty about this is that now it's also becomes easier to take this web search experience to the enterprise, because these kind of insights, results don't rely so heavily on web metrics like PageRank, but they mostly rely on just text, which every enterprise has. So let me maybe share a bit like a demo to give you a flavor on what we are working on. So this is like a quick demo of a search engine. For this demo, I uploaded a couple of financial documents from NVIDIA. And what we can do now is basically querying different kind of questions that help us understand the business performance maybe in the last year. So let's maybe start with something obvious. How high was the revenue in 2019? In the background, we're now querying with a BERT-based model. And in addition to our ranked results here, we basically get our like highlighted answers, which you could, of course, also present in a different way, display in a chatbot or whatever. And here we see already, okay, the revenue in this fiscal year was around $12 billion. Let's now maybe ask for something slightly more interesting. What were the main factors impacting this revenue? And here now we see like really now, I would say like NLP, where we need to understand what this question kind of implies. And we find here in one text snippet that the revenue was driven by infotainment modules, production drive platforms, and development agreements with automotive companies. And you can scroll a bit further down and then basically get quite some overview of what kind of factors impacted this revenue. And this is like what our clients use to actually dig through data, not only in the financial domain, but also all other kinds of text data. So in this talk, I would like to look a bit behind the scenes and give you a very quick overview of the components that are involved in building such a search engine. And we'll start with language models as really the core behind it, then go to the say more simple task of question answering, the basic form of question answering, and then talking about how to scale that actually to large data sets and industrial applications. So I guess many of you are aware of this guy, BERT, as Nathan also mentioned in the intro. I think was one of the main drivers for this heavy boom in the last year or last 1.5 years in NLP. It's basically a model that was pre-trained on a large corpora of data, mainly wiki and some open books. And the beauty of that is you don't need labels. So similar to the previous talk, this is a raw, let's say, unlabeled data, and you use a self-supervised learning technique to actually learn something about the language. And then the interesting part is after this pre-training phase, you can take this model and apply it for a couple of different downstream tasks, a big variety of downstream tasks. And it turned out that this approach works very well, and it outperformed a lot of benchmarks back then. And I would say, yeah, probably today or right now, it's still like, I would say, a modern baseline model. It's not the SOTA for many tasks anymore, but it's became kind of the baseline. And if you come up with something new, usually try a BERT model and try to compare to that one. Yeah, in these last 1.5 years, a lot of new architectures were published, basically inspired by BERT. I don't have the time, I think, in this talk to now go into details, but I will share the slides afterwards if you're interested. Maybe just to highlight a few trends that we see. Obviously, using more training data helps, like having models like Roberta big on that. Varying the training objectives from like, getting rid of the next sentence task, next sentence prediction, or more lately in real Electra, making the language model, the master language model prediction task more difficult. This is definitely one trend. And then for us also very interesting cross-lingual training, going to other languages. This is also, I think, super useful and very promising direction. So this is really the core ingredient, one of those models for our question answering task. We still see sometimes BERT as a quite powerful model, but these days also Roberta, Electra play quite a big role in our work. So let's talk about question answering then. If people talk about question answering, they usually refer to a style of question answering which is also called extractive QA. And this task is basically that you have a question, you have one single text passage, which is usually not that long. And then you want to identify a span in this text, which is then your answer. So that means the answer must really be somewhere written in this text, and you have to basically select this span. This is the most prominent type of QA. And the challenges for this type of QA are basically that obviously you have to, in order to predict an answer, this depends on the text and the question. And there's a heavy interaction of these two inputs. So you really need to understand the question in the context of the text that you have to find a good answer that you want to give out. It also means that you have a really large set of potential predictions. It's not like in a classical classification setting where they say have 10 different options, 10 different classes that you want to predict. But here we rather have like a lot of different spans that are potential answers, and it's a very large solution space. Last but not least, you need some kind of contextual understanding. Of course, not in the human sense, but you need to really relate text in question in a quite advanced way, I would say, to give meaningful results and give meaningful answers. And I would say currently best practice and the most popular approach to deal with this task is to model this problem as a token classification task. So that means you have a model that for every token predicts basically if this is a start of the answer or the end of the answer. And in the end, you basically combine quite greedily the best start with the best end token, and then you have your span. So this is a pretty, I would say, simple, simple way of modeling that, but it turned out to work pretty well in practice. Then you can take one of the mentioned language models, BERT, Roberta, or whatever, and fine-tune this on a labeled question-answer dataset. And this model is then also called usually a reader. A popular dataset to do that is SQuAD, but there are many more actually to do that. Why now? So why is question answering coming up now? And I would say like even in the last year or half year, it really accelerated crazily. One big reason for that is actually that these transformer models came out, and transfer learning really is really working now in NLP, and they boosted the accuracy crazily. So here you see the SQuAD dataset, F1 score over time, and here late 2018, that's basically where BERT was published and caused quite a big jump in the performance. And I think that caused crazy excitement in the community and also in the industry. So from our clients, we really see a high demand for these kind of solutions. So they're kind of pulling this technology because there's more and more information workers, and they of course see that as a nice way to improve their efficiency. And on the other hand, they're also, I think, a bit in a competition with the web search experience. Yeah, we all experience that, I think, every day, like how that works in the web. But if you then go into an enterprise and think about the search in some Drive or maybe even in Slack, that is still like quite a different experience. Or in a PDF, it's a Control F and you look for a keyword. It's very far away from the web search experience. And what we also see is like a big momentum right now in research. Just in the last half year, there's been a great body of research, a lot of excitement, a lot of work in conferences, also going now in different directions, not just this pure span-based QA. There's a lot of work on reasoning and synthesis. A lot of new model architectures applied to this problem, taking it to other languages, and all that. I think is a great area, a great problem to work on these days. So we are really super excited about it and see a big future for that. Yeah, here there are a few data sets. Again, I will share the slides. Maybe it might be a good starting point for you. Today, I just want to highlight SQuAD is the big data set, most common one. There's a lot of different varieties out there. For us today, we'll talk about scale. So how can we actually now take this question answering technology and scale it to really industrial use cases? And also for that, we have a couple of data sets out there. So let's talk about scaling. The task of open domain QA is very similar to the one that I shared before. The only difference is that you're not querying on a small passage, but you're querying into a huge collection of documents, usually some kind of database, and you want to find the answer in there. And this, of course, brings some new challenges to our problem. First of all, these reader models, they usually have a limited input length. So if you have long documents, you somehow need to split them and feed them one by one into the model. This causes then problems with the speed, and also a problem of aggregating these predictions then again in a meaningful way. The most popular approach right now to deal with this is that you have a so-called retriever-reader pipeline. And this retriever-reader pipeline looks like this, that you have a document store where you have all your documents, and you pass all those to a retriever model. This retriever model is a very fast, simple algorithm in the usually, which identifies some top K candidates where the answer might be in. And then you actually feed it into this more expensive, more powerful reader model, for example, a transformer, to then really identify this answer in detail. And with that approach, just on an exemplary data set with around 7,000 documents, if you would just take this reader approach, this plain vanilla QA approach, you would take like ridiculous more than 3 hours per query. With this retriever approach, you can get that down to less than a second without having too much of a drop in performance. And this is like the exciting part now, and having here really efficient retrievers, that's what we are working on. Here, if you're interested, there's a couple of very recent research papers who are just dealing with this new challenge of finding good retriever models. I can highly recommend the last one here, dense passage retrieval, just came out a few weeks ago from Facebook people, and they have a really nice new benchmark, really good, really promising, and the approach that they take is also quite, I would say, simple to implement. They basically have two encoders, one for the question, one for the answer. So basically have two embeddings, two vector representations for both parts. And this is something you can easily then pre-compute and use for a very efficient retrieval step. I think I won't have time to go into detail about this paper, but just as a highlight, I would say the most interesting part there is they have a very interesting sampling methodology using in-batch negatives. If that's interesting to you, maybe in the question part, steer that yourself if I should talk more about that. What I want to highlight is that this is out there. We believe in open source, and we believe people should try that out. And if you want to do that, we have a framework called Haystack, where you can basically build these pipelines that I just described, having a document store where you index these documents, can use a variety of different retriever methods, and then afterwards a reader, which is basically compliant with for example, Hugging Face Transformers framework or a farm framework, and also other popular open source libraries out there. We really believe that these kind of framework should be modular, easy to extend, so that you can stick together your pipelines as you wish. And yeah, for us important, we don't build like research code, we build code for production. So that all comes with some REST APIs and Docker for deployment. If you're interested, check it out. We are always happy to also get new contributors, but also happy to support in maybe your first steps in this QA direction. That's it already from my side. Only then to summarize the main points from this talk. Transform models are key to enable extractive QA for practical applications. But these industrial search applications really require this open domain QA style where you have like hundreds, thousands, or even more documents. For this open domain QA, these retrievers are currently the best practice and work really well. And you can implement all that yourself via Haystack. That's it from my side. Happy to get some questions then.
I guess just a more general question and a bit less on the NLP, but given that you're working with an open source framework, what have you been, and we're also building a community with London.AI, what have you found as the best methodology or overall processes to build your community and get contributors to actually work with Haystack?
Yeah, I think one thing is definitely like events like this, going out there on conferences. That worked very well for us in the past. And then what we really believe is in like early, like really engaging within the community, like in GitHub, for example. So if we have people, we have a lot of people who joined first, just trying it out, having some issues, and we then converted them or turned them basically to very active contributors, and so that they are now actually answering questions. And so we think we really believe in growing that organically and really concentrate on in the early stage to make people happy and to understand what type of problems what they have. And yeah, for us as a startup as well, that's super important learnings, because in the end we want to build some nice software, and this is very relevant feedback that we get from the community.
Got it. And so Nathan's posted your GitHub repo, so if anyone wants to get involved, make sure to check out the comment section. Just a question from Nathan Smith. Could you expand a little bit more on the retriever model and negative sampling, if there is time? Which there is.
Yeah, sure. Maybe let me just share my screen again. Yeah, so basically this technique is from this mentioned paper, then special retrieval. And yeah, their approach is that they have two encoders, two BERT-based encoders, which create embeddings. And that's, I think, like recent evidence, I guess more and more evidence in research that it's for this type of problems better to have two independent encoders rather than just one model to encode both text parts, because they are very different in their nature. And in this particular paper, what they're doing is they're training that on samples which consist of one question as an input, then one positive passage, so one passage that actually includes the answer, and then n times negative passages. And they are experimenting with different strategies how to sample these negative passages. First, they try random sampling, which is, I think, the most obvious one. But then in the end, they have a method which is called in-batch negatives with gold passages. And this is basically, these gold passages are other passages that actually include answers, but to different questions. And in-batch means in that sense that you, say, have a batch of 100 questions and passage pairs, and you can now reuse as negative passages the other 99 passages that are in there. So this is like just a very nice way of making this more efficient, that you don't have individual negative passages, but rather reuse what you already have in your batch. And yeah, this is what they're doing. Plus, they put one other negative passage in there, which is basically the best candidate from a BM25 retriever, which is not containing the answer. So it's like, I think, a quite tough negative example that they merge in there.
Okay. And just because we're a bit short on time, I think we might have time for one or two more questions. So I'll try to pick on people who haven't been chosen yet. One by Jasper Coyd, which is, as you develop solutions for enterprises, given how rapidly NLP is developing, how much technical debt is there, and how much rework is needed to incorporate the latest state-of-the-art systems?
Luckily, we are quite a young startup, so far we don't have that much of a technical debt. We are there for now 2 years, and I mean, of course, quite some things changed already in that time. Yeah, I think for us, it helps that we also do open source, so that we also have like contributors getting in new models, latest technology, to actually get that into the enterprise. It really depends on the enterprise. We've seen companies who are really fast also in then applying new things, getting new releases out there. And of course, then there are slower moving organizations where it's sometimes trickier to get updates in there. The good thing is that, from my perspective, the pipelines have are more standardized these days than probably like 5 years ago or 2 years ago, because we really have this transfer learning paradigm. And in the end, if I now replace a BERT model with an Electra model, that's very good, very well handleable. It's one line of code that I change, and the rest is pretty much the same.
Great. Well, thanks a lot for that presentation. And of course, as I mentioned, we posted information on how to learn a bit more about deepset for our community. I'll let Nathan give an overview of the RAAIS Foundation and why we're all here today.
Cool. Thanks.
Great. That's good. Thanks, Alex. So, can you see my screen?
Yep, we can see your screen.
Okay, cool. Yeah, so as Alex mentioned, we run these events in support of open source AI education and also open source code projects. And so when we run in person, we kindly ask that everybody donates just £5 towards this foundation that we set up that is currently funding projects in privacy preserving machine learning and also in energy and climate. And we're looking for many more projects to fund that will hopefully spur the community forward and create tools that everybody can use, whether it's for startups or NGOs or universities and bigger companies as well. So if you enjoyed the show tonight, we'd really like it and appreciate it if you could head over to RAAIS.org/donate and chip in. Even £5 would make a difference. In terms of future shows, so in about a month, we've got our online RAAIS conference, which is a reminder, is about a one-day event. Typically we run in person, and this year we're going to be doing it online, much in the same format than London.AI. And we're really excited to have speakers on both sides of the Atlantic, from the US and from Europe. And we'll be covering topics in consumer nutrition and privacy and homomorphic encryption and policy and ethics, but also in designing biological systems, robust deep learning systems, self-driving cars, medicine, and hardware. So we've got some really cool speakers lined up, and we'll be conducting a bunch of interactive sessions so that people who attend the event can also chat to peers in interest groups and also chat with speakers as well. So we're going to try and approximate as much of the real-life interactions that you get from our events in person online. So we'd really love it if you can join us there. Just head over to RAAIS.co and then drop your details in the same way that you've done for London.AI. And to keep abreast with all the events that we're going to do in the future, we've got our newsletter, which you can grab on London.AI. Follow us on Twitter, and of course in the Facebook group, we'll be dropping all the live videos and also pushing them to YouTube in case you want to rewatch some of the content. And so, with that, I'd love to welcome our final speaker, Katya, who's a data scientist at LabGenius, which is a London-based company working on protein therapeutics and trying to discover brand new ones using closed cycle machine learning and empirical lab experimentation. So super exciting company, and really glad that you could join us today, Katya. So over to you.
Thanks so much, Nathan. Let me just share my screen. Can you guys see my screen? Oops.
Yeah, we can see your screen.
Okay, excellent. My internet is difficult sometimes, so let me know if you're losing me at any point. So as Nathan said, I work at LabGenius as a data scientist. LabGenius is a biotech startup that is London-based, and we're building a platform through combining synthetic biology, machine learning, and robotics to design novel protein therapeutics. And I noticed that whenever I say proteins, different people have very different, sometimes pretty vague concepts in their head. I'm a vegetarian, and my grandmother is super upset about that fact. She keeps telling me I need more protein in my life. Well, actually, I don't need more protein in my life, because proteins are behind all of the life on this planet. They're in all of the living beings, including plants. But just to add some context there, what are these proteins, right? So proteins are tiny little molecules of nanometers in size. This big guy here, for instance, on the right side of the screen, is a complex of different proteins, and it is 1,000 times smaller than a diameter over here. So you can imagine how tiny these molecules are. But despite the fact that they're so tiny, they can have various different structures and various different functions. Some of them can move things around, recognize pathogens, bind iron, just to name a few functions. So imagine we could design proteins to our needs. Imagine we could create a molecule as tiny as these guys that would do exactly what we want it to do. This would help us to cure a lot of diseases, right? And every single one of these tiny little guys could become a billion-dollar drug. How do you design a protein though? If they're so tiny, they have such small, very intricate different structures, how do you shape one and make it do just what you want it to do? Well, the good news is, if you unfold every single one of those little guys, you will end up with a linear chain composed of 20 different types of building blocks. And scientists have come up with a single letter code that encodes every single building block. So you can take any protein, be it from the lab or from a smoothie, and write it down in the form of a string that is composed of 20 different. Find a scientist there and ask them to make this protein for you, and they would know exactly what to do. Unfortunately, though, there are so many different variants, there are so many different strings that could encode the protein that you want to make. For instance, if you had a protein of only 2 building blocks, which is never the case, it would yield 20 to the power of 2 different candidates. If you had a protein of 100 building blocks, it would yield 20 to the power of 100, and the majority of proteins are much longer than 100. And if you had a protein of 27,000 building blocks, which is the longest protein that is known today, this would yield a 20 to the power of 27,000 different variants. This is insane. This is a crazy number. But have all of these proteins been seen in nature? Well, actually, if you take all of the proteins that have been found by the scientists in nature, those would only comprise a tiny little fraction of all of the proteins that exist today. And those would comprise a tiny fraction of all of the proteins ever, because there have been a lot of proteins in this world that didn't survive to see the light today. And those in turn would only comprise a tiny fraction of all the protein sequences that are possible, which is essentially an infinite amount of different variants of proteins. So how do you think about this infinite space when you want to design a protein? Scientists have come up with a beautiful metaphor that I personally really like. It's not too mathematically accurate, but it gives a nice framework of being able to comprehend this huge number. So if you take all of the variants of a protein A, say that has a length of 117 building blocks, whatever, and you take them all and you map them out on a 2-dimensional surface, where each dot would correspond to a protein variant, and all of the adjacent dots would correspond to similar variants. So the further away you go from protein A, the more different the protein becomes. And then you add another axis that would tell you how good each variant is. This would give you a sort of a landscape. And this landscape is referred to as protein fitness landscape. So when you're designing a new protein, essentially what you want to do, you want to find the peaks on that landscape, and you want to sample from those peaks. How is protein engineering done today? Well, the classical way is to use directed evolution, which is essentially mimicking the evolution that we all know. By introducing random changes and then see whether these changes are good or bad, you're randomly moving across the landscape. And just to understand how inefficient this way is, imagine you go on a hiking trip back when it was possible. And then you don't have a map of the terrain. You don't have Google Maps, no maps. And then you have a lot of thick fog around you. So you have no idea where is the peak that you want to go to, which way do you go. Only making step-by-step iterations, you will be able to find it. It will take you ages. What would be a better way? A better way would be to have a map, and preferably a Google map that also would tell you where you are at every single time point. Then you would know exactly where the peaks are, and you can go directly there. So for designing a protein, it would be nice to have a map of the protein, the corresponding protein fitness landscape, to know where the peaks are. Although it is not really possible today, we believe that the way forward, the framework to think in order to be able to achieve that, is called empirical computation. It has 4 steps, and I'm going to talk you through those. Step number 1 is constructing a number of protein variants, physically making the molecules. Step number 2 is testing the molecules in the lab in order to rank them according to their performance. Step number 3 is using machine learning in order to extract the mathematical relationship between sequence and performance. And then once you have that description of the relationship, you can use it in order to design and inform the next generation of your libraries of a protein. So you could go in this iterative sort of circles until you found a protein that does satisfy, or a set of proteins that do satisfy all of your needs. Well, now we have a framework. What is the main challenge in designing a protein therapeutic? Unlike designing a protein, you don't only want to optimize for one feature, you actually want to co-optimize for several features, because you don't want to, if you have a toxic protein, you don't want to go anywhere near a human body, right? So imagine you were designing this molecule and you managed to hit 9 out of 10 different parameters, and they're all great except for toxicity, which is skyrocketing. obviously this protein is not going to go to market. It's not going to become a drug. So all of the resources that you've spent on developing this protein are going to be binned. And when I was talking about the protein fitness landscape, I was simplifying the concept to some extent. When I was talking about fitness, it's actually not just one axis. It's a combination of lots of different fitness landscapes that give rise to the goodness of the protein in your specific case. So the way we address this in our platform is by starting with protein designs, but then decoupling the different properties and designing tests and machine learning models specifically for those properties. And then once we have the machine learning models for all of the properties of interest, we use multi-objective optimization to inform the next generation of protein designs. Now that we have an overview of how empirical computation works and why engineering a proteins is important, let me give you 8 easy steps in order to be able to design an empirical computation platform for protein engineering. Step number 1, as I said, you have to build a library of proteins. And one of my favorite things about contemporary molecular biology is that essentially it works like Lego. And I used to love Lego when I was a kid, and I know I'm not the only one. So if you had a protein of this sequence and you wanted to create a library that would contain proteins that carry a full combinatorial set of all of these 3 mutations, then what you need is the original protein, your mutations, and then some reagents and a nice pipeline that combines these mutations together. And what you will end up with after some incubation is a protein library, and those proteins would carry the full combinatorial set of those mutations of interest, which is pretty neat. Now you need to test these library of proteins. And as I said before, we're designing specific tests for every single property that we're interested in. And those tests are designed to perform as filters. So the better the protein is, the more likely it is to pass the filter. So for instance, here, if you take the orange protein, you can see that it was quite abundant in the input library, but then it only became very, very rare in the output library. So by comparing the abundances of the protein variants in the input library and the output library, you can infer how good each variant is. So you can rank these proteins. But up until now, all of what the human scientists could see was a tube with transparent liquid as the input of the filter and a tube with transparent liquid as the output of the filter. So now we need to make the data computer and human readable. We do this by using these amazing machines that are called next generation sequencers. They're called sequencers because they can transform the physical molecules into sequences, so strings of text, and they're called next generation because they can read millions of physical molecules simultaneously. So we end up with a lot of data, and we need to process the data. As fantastic as these next generation sequencing machines are, they do make mistakes, as any biological system, biology-based system. So we have a pipeline to process those reads, pre-process those sequences that come out of the NGS machine, next generation sequencer, and it's all based on Google Cloud Platform. It's kicked off automatically, and then in the end, we have a clean table that is composed of lots of different strings, which correspond to protein variants, and then the relative abundances, so rankings of the different protein variants. Now, finally, we can model the data, right? Because we have the input and we have the output, and we want to link the two together. And just to remind you, why do we need machine learning at all? If we have tested everything in the lab, what does machine learning bring to us? Well, actually, we haven't tested everything. If you remember, the sequence space is massive. And even within the fraction of the sequence space that we had our high interest in, we didn't sample all of the dots. So imagine we sampled these green dots scattered around here, and I want to use them together with machine learning to reconstruct the actual fitness landscape shape and to identify the peaks. What would be the easiest case scenario in the sequence to function relationship? The easiest case scenario would be if the relationship was linear. If every single position had a linear impact on the fitness of a protein, on the goodness of a protein. Plus some random noise, because biology is super noisy. So if you one-hot encode your data, you have your rows, then you can use a simple linear regression to assign the weights, and that's it, you're done. Well, actually, we know that mutations interact with each other. Remember how I said that the protein has a three-dimensional structure? Obviously, the positions would impact each other. So the relationship is not linear. And we need to add some non-linearity to the equation. The simplest way would be to say, okay, well, let's add all of the interaction terms here. And then we also need to assign weights. So it would be a pairwise, triple-wise, quadruple-wise, all sorts of wise interactions. Obviously, this would expand massively the number of features in our data set. So instead of that, let's take the linear combination of mutations as we had before, and let's wrap it into a non-linear function. Scientists call this linear combination of mutations fitness potential over sequence. And the reason for that is that this is your, essentially, this is your linear variable that maps the sequence space to the fitness space, and it shows what is the potential of the sequence to be fit, to be good. And now we need, if we have this equation, what we want to do now, we need to come up with the weights simultaneously with a nonlinear function that describes the relationship. And what is the machine learning way that could allow us to co-optimize the feature weights and the nonlinear function? This is the good old, very simple feed-forward neural network with only one neuron in the first layer. Because one neuron in the first layer, we still have our data one-hot encoded, would already give us the linear combination of mutations, and then the rest would add nonlinearity, the nonlinear function, to the equation. And this is a beautiful experiment that we did with the fantastic lab at IC Austria Kondrashov lab, where we took a protein, we tested lots of different variants of that protein, and then we applied the simple feed-forward neural network architecture. And we saw that not only our accuracy was pretty decent, but also the shape of the function turned out to be a sigmoid, which is very interesting because depending on where you are, what your fitness potential are, so what is this, the rest of the sequence, the same mutation can have a very different impact on your fitness. And then obviously you don't have to limit yourself to one neuron only. You can go two, you can go more. And we saw that adding more for some proteins, or for many proteins, does indeed improve the accuracy, the prediction accuracy. But keep in mind that the more linear combination of mutations you have in your equation, the more high-dimensional interactions, the more dimensions you need to explain the sequence-to-function relationship, and the more interesting your protein is. So now that we have the models, we need to optimize our original protein to perform fantastically for all of the properties that we have in our interest set. And basically, we use multi-objective optimization, as I said before, to co-optimize the different properties simultaneously, and then to select the best performing mutation, the best performing sequences. And then we use those sequences as seeds for the next generation. Finally, everything up until now was done in high throughput, and you can't really make a drug based on the high throughput tests only. So we need to test the predictions in a low throughput, on a low throughput scale. And we're lucky because we have a whole protein team that are devoted to carefully extracting lots of different proteins and then analyzing carefully their characteristics. And the way to do that, in order to carefully analyze proteins, you need to produce a lot of those proteins. So we do that by using E. coli, Escherichia coli, the bacteria that lives in our guts actually. And scientists exploit this bacteria a lot. So you basically feed the sequence of your protein into that bacteria, and the bacteria produces a lot of the material that you want to characterize your protein in. And then once you have that, you can go on and do your sophisticated tests and make sure that your predictions correspond with reality. And then finally, you need to automate every single thing that you have built, all of the pipelines, because humans are not really happy when they're asked to work after hours, and robots can work 24/7. They don't make mistakes. They record everything they do. And this allows us to be more efficient and at running the platform. So if you have missed the majority of my talk, I'm going to summarize it for you very quickly. At LabGenius, we're combining synthetic biology to create protein variants and test the protein variants. We use the tested sequences and machine learning to reconstruct the sequence to function relationship. And we use multi-objective optimization to find the best performing sequences on the fraction of the fitness landscape that we have scanned. And then finally, we use automation to make it possible for our platform to run 24/7 and learn every day. Of course, there are a lot of fantastically smart individuals behind this platform, and I'm honestly super lucky to be working with these guys every single day. And finally, I know these times are quite uncertain, but we have a number of quite exciting openings on our website, including a computational biologist who would join the data science team. So do definitely check out the job openings, and thank you very much.
Thanks a lot, Katya. For people in the community who haven't worked with biology or life sciences before, but have been working on data science and machine learning for a very long time, how easy is it to translate into your domain? And are there some like prerequisites or tips or challenges that people might face?
I'm so sorry, Nathan. I can't find you anymore. Sorry. Yeah, there you go. I'm back. Could you repeat the question, please? I'm so sorry about that.
Yeah, sure. I guess like the universe of people who've done both biology and machine learning is pretty small. Obviously, we'd like to have more people come into the field. So for people who are more on the machine learning side and not biologists, do you have suggestions or tips for people making that jump, if this is something they're interested in doing, or is it just too intimidating and they shouldn't try?
That's an excellent question, actually. We have a number of examples on our team of people who have never learned biology except for in high school. And then they came in and embraced the uncertainty that comes along with experimental biology, and they learn from scratch. So it's definitely possible. And it's always interesting to work with people from outside the field, because you know, when you have been in the field for too long, there are certain things that you assume, and then people who come from outside, they ask relevant, unexpected questions that help you reflect back on the things that you have assumed for such a long time. I think the main tip is embrace the uncertainty, and as long as you're really, really keen to learn, it's definitely possible. And all of the people on my team are, like all of the academics really, I feel like, and many of them are ex-academics, are really excited at any learning opportunity, teaching opportunity. So it's quite a smooth process, I think.
We saw in Malte's talk like this huge kind of model zoo of new NLP approaches to like language modeling. Has any of that like made its way into your technology stack, or are you evaluating or considering any of that?
That's an excellent question again. We are definitely. There's been a number of very interesting papers in the field where people were learning the language of proteins. And you can imagine, like the things that I was presenting were depicting the sequences in a binary matrix way. So the models that were built here had no idea of the concept of a protein, right? So they only know, oh, this is 1, this is 0, whatever. In order to be able to transfer the knowledge between different projects, you need to come up with a way of representing the proteins in a meaningful and also a uniform way. And the NLP models, BERT as an example, have shown a lot of potential, and we're definitely working in that direction as well, in order to be able to transfer the knowledge between different projects that we're running.
Awesome, awesome. I think we have so a few questions in the chat. So one's from Javier Miguel. He says, hi, great talk. Why so many of the protein trials that you've measured have 0 measured fitness, I believe in your step 5? Or I guess maybe, I don't know if it's 0 fitness absolute, or maybe they just have poor fitness. So I guess like maybe the question is like, why is there such a big diversity in terms of fitness scores?
If that was about the slide, it was just an illustration administrative purpose.
Okay.
But in general, I can say that the majority of mutations, if you introduce randomly into a protein, the majority of mutations will break the protein. That's why you have to be quite strategic about which mutations you introduce. Sometimes it can happen so that you introduce, if you introduce a mutation on its own, it would break the protein. But if you introduce it together with another mutation, it would allow you to pass to the other peak. Generally, although the ridge that I showed had a lot of peaks, normally there are a lot of death, so the so-called death valley. So a lot of sequences, if you just pick randomly out of the blue, those most probably will not be functioning at all.
We have a question from Orest who says, we're asked how many sequences or mutations you produce in the wet lab to get a reasonably good machine learning model? And related to that, do the models generalize across different proteins, or do you have to retrain or recollect data for different proteins?
Excellent questions. I'll start with the first one. It really depends on the protein that you're working on, because different proteins can have very different sequence to function relationship, obviously. Some of them are really simple, like with GFP, and some of them are more intricate than that. So generally, we see that about 10,000 protein variants for like a normal protein would work in order to be, but this is also like there's a detail there, because you need to think about how wide of a sequence space do you want to cover? Because there is no magic here, right? You can't just, using 10,000 training sets, you can't, training sequences, you can't predict all of the protein fitnesses in the world. So in order to be able to produce a model that covers, say, 10 to the power of 9, 10 to the power of, well, 10 different sequences, you need approximately 10 to the power of 5 different variants of a protein. I think the next question I have already covered when I said that you need some sort of a translator between different sequence proteins in order to be able to, embed them into the same space. Otherwise, they have their own dimensionalities and their own spaces. And the third question was?
That was it. It was just about how many sequences you need for the model to be good, and then can you generalize? Awesome. Thanks.
Awesome. Well, I think that kind of closes it for the evening. But thanks again, Katya, and to our 2 other amazing speakers. That was definitely very insightful. Great. Well, if this was your first London.AI, we hope we'll have you again for the next one. As we mentioned, we'll be doing a few in this format. Easiest way to find out when the next event is to sign up to our newsletter on London.AI. Follow us on Twitter, and if you think you have friends who might enjoy this as well, then make sure to share this with them. 2 quick things. As Nathan mentioned, sign up for the big event, which is in a month. You can do that with the URL that was posted before. And if you enjoyed our show and you'd like to donate something, again, use the URL to the RAAIS Foundation that was posted before. I'll post it again just so it's at the bottom of this link. Thanks again to everyone, and enjoy the rest of your Thursday evening. Bye.